Shall we?
Yes.
Are we? Oh, okay, we're recording. Hi, everyone. Today we have the last seminar of the high energy theory seminar series. And we are very happy to have Yikun Jiang from Northeastern University telling us about building up space-times with BCFT. Uh, please.
Thanks, Nima. Thanks for having me here. I'm very excited to present to you this work. Mostly, I will be mostly focusing on this second paper, which we wrote with Ling Chen, Janet Han, and Bingqing Lao. And there's a shorter version if you want to read like the top line. So the idea, let me briefly mention our motivation. So since the brilliant discovery of ADS-CFT correspondence, we understand really a lot about ADS quantum gravity. But there is a crucial problem. I think it's still quite mysterious how the geometry or gravity emerges from the algebra data of CFT. And there are some results currently. I think it's very popular to study the large n limit and use like linear algebra techniques. And today I will actually there's another aspect, especially in 2D where 2D CFTs are very well studied, and we can actually go further. And especially a question we have in mind is how to really reconstruct the bulk, especially including the background metric. Um, because usually when people talk about like bulk reconstruction, people talk about reconstructing the operator on top of a fixed background. And today I will show you actually there is even a way to reconstruct the whole bulk. So I would say that when ideas try to make sense of these stuff relating to bulk and boundary is really coming from the analogy between the root-Takanagi formula and the tensor networks when people start studying calculation of entanglement entropy. So let me briefly review what it is. So the root-Takanagi formula is telling you I have ADS CFT, the CFT lives on the boundary, and there's ADS quantum gravity in the bulk. So if I want to calculate entanglement entropy of a subregion A, what you do is you try to find in the ADS bulk a minimal surface. And then the area of that minimal surface over 40 Newton will be equal to the boundary entropy. And this looks a lot like what condensed matter physicists use to study the tensor networks. So the idea of tensor network is as follows. So we use these tensor legs to represent the ground state of some Hamiltonians. And in general, it can be it has this tree this tree-ish structure. And when you calculate the entanglement entropy of a ground state represented by these dots, what you do is you try to find a minimal cut through the bulk and try to count the number of links through that cut. The minimal one will give you the correct entanglement entropy for the ground state. And this looks a lot like the root-Takanagi formula. And Brian Swingle noticed this and proposed that maybe there really we should use tensor networks to understand how actually geometry emerges from the CFT data. And this also is one of the starting point of the whole it from cubic program. I will show you actually entanglement play a very huge role in this building up of quantum spacetime from CFT. And furthermore, I want to say that there is an extra dimension emergent from CFT, and we kind of have a intuition that dimension because when you study the metric, you can see that it's changing the energy scale. So it's very natural to say that the bulk direction is related to some kind of RG flow. And I will show you actually that intuition is exactly correct. So to make this intuition precise, people have tried a lot of things to make toy models that represent properties of gravity. I'm showing you three of them. All of them are great. They have some properties of gravity, but I would say that they are not gravity, they are also not CFT. They capture something of the ADS-CFT correspondence, but not everything. But today I will show you actually, by studying CFT2, there actually is a step-by-step procedure that build up the CFT2 at the same time a quantum space-time for ADS3 using what we call the BCFT Legos. Okay, this is a cheap diagram. Like you have Legos, you really imagine like putting them together, and layer by layer you build up a bulk, which is the ADS space-time. And I will show you actually this is an exact analytic space-time tensor network, which is different from the usual time slice tensor network. I will also explain the connection between the two. But really, this tensor network is nice because the tensors here we use are algebra data of the CFT. So you can actually see how geometry or gravity emerges from algebra or CFT. And specifically, I will use Liouville theory as an example where actually the mapping and how they correspond to each other is extremely clear. Okay. And finally, I will tell you that in this procedure, you can actually see that this emergent bulk direction is indeed related to an RG flow, and it's a very cool RG flow that's related to what people these days are very fascinated about, which is the non-invertible symmetries. And this, especially the RG flow, is symmetry preserving. Okay, so with that in mind, let me really go through them step by step. That's the procedure we write our paper actually. So the first step is let's forget about yes. Let me just tell you a new way of calculating CFT path integral. And if you view it this way, you will see the bulk actually. So the idea is as follows. So in I will focus 2D and a common something on higher dimensions in the end of the talk, but let's focus on 2D. So in 2D CFT, we usually calculate the partition functions or correlation functions using the so-called closed pair of pairs decomposition. So what you do is you cut the manifold open into these pair of pairs. These pair of pairs, you can think of them as 3-point functions. Then what you do is because you cut them open and you want to glue them together, you want to insert complete basis on these circles. And once you do that, you will recover the partition function. For example, this is a genus 2 surface. Okay. I will first tell you actually there is another method to calculate this, which was not appreciated before. And that actually is very much related to the emergence of geometry and tensor network and the local structure of CFT and ADS. So really what we do is instead of cutting them into closed pair of pairs like this, we're actually, for genus 2, there is only one way of cutting, although you can say the lengths are different, but really you cut them into two closed pair of pairs. But now there is a way to cut manifolds open, 2D manifolds open, which are use triangles. So you just triangulate your 2D manifold. So this arbitrarily you triangulate that, and now this is full of triangles. So for a path integral, I want to sum over all the contributions on these triangles and insert these basis of states. But now notice that because now I cut them open, the triangles, the states are living on these lines. And for lines, really, you need to specify boundary conditions because it's an interval if it has boundaries, no longer circles without boundaries. So when you specify boundary conditions, I will dig a hole here. And the meaning.
Can I ask a quick question? Sorry, you were
Yeah.
talking CFTs and then you start drawing these 2D manifold. These are Euclidean partition functions. Is that how you're
Yes.
thinking?
Euclidean partition functions or correlation functions. I'm drawing a partition function, for example. That's
You
oh,
call
you're
them
muted.
correlation functions because you puncture them?
Yeah, you can insert functions exactly. Yes.
Okay, so these are basically punctured Euclidean path integrals. Okay, thank you.
Yes. But for simplicity, I will focus on partition function, which does not have punctures, but you can include punctures indeed. Yeah. So for a fixed boundary condition, these holes cannot be closed. I will just explain to you immediately. But the idea is, so first you keep these holes with a fixed boundary condition. And then when you fix the boundary condition, you can insert complete basis of states. The boundary conditions will be labeled by sigma always in my talk. And the complete basis of state include the primary labels and the descendants. So I will just sum over all the contributions of these tiny triangles with all the primary descent fields propagating along these lines. And then we find a way to close up the to reproduce the original partition function. So in this case, as you can see, it's a triangle, so it's no longer a closed pair of pairs, just look like this. Now they're lines, so it's open pair of pairs. If you have seen this in Puczynski, immediately remember that. If not, then just think this is a pair of pairs where initially you have two boundary conditions, A and C. There's a state in the middle, and then it becomes two different states with boundary condition A, B, and BC. Okay. The path integral on these chipped triangles, really the tiny hole here is for regularization purposes, because Now I'm just leaving there because there really is a hole. You cannot just shrink it without leaving any imprint. So I will just put it there with a tiny size epsilon. And these chip triangulation contributions can be calculated by a conformal map. You map this into the upper half plane. Then on upper half plane, this is the familiar formula. Usually it's not chiral because it's the full plane. Now it only the Hilbert space is on a line, so you only have a chiral half. So this is these deltas only have a chiral copy, and it takes exactly the same form. Now there's the OP coefficient now has 6 labels because there are primaries and the boundary conditions. And I'm suppressing the descendant because this is the one for the primary fields. And for descendants, you just use the conformal symmetry to fix it. Essentially, just for example, the first the L minus one, you just add derivative to it and then pull it back to the original triangular shape. So all the contributions can be calculated explicitly. So for simplicity, I will introduce a notation, which is I call these contributions T associated to each triangle. So now I've told you that there is an OP coefficient, and there's a piece that depends on the shape, the positions, and whether you have descendants or not. But for a conformal family, which means for different descendants, but for fixed primaries, these coefficients are the same. So they factorize look like this. So I will always denote these contributions by T, and I separate out the OP coefficient piece and the position dependent piece, which are actually conformal blocks that I will explain. Like currently, they are just 3-point functions with the position dependencies. They are not yet conformal blocks. Blocks come into play when you sum over descendants. And I will tell you that this is what we call the Legos. I will use these pieces to build up the CFT partition function and the ADS spacetime. So we
Sorry.
also invented this. Yeah.
So can you say again? So this curly T is what exactly? So there's an OP coefficient,
It's just the path integral evaluated on this tiny triangle.
and how is it labeled? So
Yeah, it's labeled by 3 boundary conditions, sigma 1, sigma 2, sigma 3, and 3 primary labels, alpha 1, alpha 2, alpha 3, and the descendants I1, I2, I3.
so if it's a triangle, I should think of boundary conditions on every line, right? Every
Yeah,
edge.
correct.
And so are those alpha and i's?
No, the alpha and i's label the primary fields. It's like this. What you have in mind is you count, yeah, because this is a CFT. When you conformally map it, you can think of now it's a state. You can think of it as using the operator state correspondence. It will correspond to a operator, right? So when you map it to the upper half plane, it become an operator.
For sure, but which operator is it? Are you labeling it by alpha and I or?
Good. So each operator, for example, this operator, I will label it by phi alpha 1, sigma 2, sigma 1, and a descendant label I1.
I'm just confused in the sense that are these the capital phi's, are these primaries?
Yeah, the boundary primaries.
What are
Boundary,
the labels alpha and sigma for primary?
the primary, it's the label of the conformal dimensions, just as the closed
But
case.
isn't it just two numbers, H and H bar?
Yeah, exactly.
These are global primaries.
No, they are Virasoro primaries
So it's just H and H bar. Why do you have three there?
because they have boundary conditions. The primary fields also depend on boundary conditions. Yeah, I guess if you're not familiar with BCFT, it might not be familiar
No.
with
Sorry.
because
It's not a statement about BCFT.
yeah,
I'm saying that you write phi as an operator inside your correlation function.
yes,
Is that the Virasoro primary?
yes.
The Virasoro primary is labeled by H and H bar. There's no other thing, right?
No, only there are still primaries living on like the okay, good. The boundary, these are strictly speaking, they are called boundary condition changing operator. So they really
The
also depend on
boundary condition changing operator. I got it. Okay,
yes,
thank you.
yes. That's the more proper way of calling it. Yes. Yeah, good. Yeah, thanks. It's actually very important. Like just interrupt me if anything is not clear. Good. So Yeah, when we have this now, I will tell you, we first fix the boundary conditions, which means when you fix the boundary conditions, these holes are actually still there. But I sum over all the primes and descendants. So fix boundary conditions, but I insert complete basis of states. So I get this formula. Just to mention, this actually, when you sum over descendants, you already see that when you glue two triangles together, this is just the usual notion of a conformal block because I have OP coefficients and I have states that propagate uh, in this beta 2 edge, and I sum over the descendants. This is a conformal block, and also a chiral one because it's a BCFT. Okay, but really, this gives you the partition function with a lot of boundary conditions because I specify the boundary conditions on these tiny edges. Now, to really recover the original partition function, I have to finally close these holes. So, but actually, if you specify any boundary condition, conformal boundary condition, actually they don't shrink because the naive reason is because you can go very close to these holes. Then very close to it, you have a state living on the circle. And this circle, usually, it's a boundary state. In boundary state, when you preserve boundary condition, it will be called the Cardy boundary condition. And they're not the vacuum. Shrinkable means you want them to be the vacuum. So they cannot be shrinked. However, there is actually a very interesting way discovered independently by Janet, Gabriel, and Ronco and his student that actually you can do something that modify this a little bit by weighted sum over these boundary weighted like boundary fixing boundary condition partition functions. And the weight is chosen such that currently is ad hoc. I will just call it omega. If you know CFT or TQFT, these are proportional to the so-called quantum dimensions. If not, just forget about it. It's just the coefficient, some coefficient we choose. And the coefficient has the property such that when you view in the dual channel, the weighted sum of these boundary states will become vacuum and all its descendants. But now as the hole get very tiny, actually only the vacuum state will survive. The descendant will be all suppressed. And it survived with a universal coefficient, e to the pi c over 6 epsilon. This tells you that the original path integral, if I do this weighted sum with a divergent factor removed, I take the epsilon goes to limit, this exactly reproduce the original partition function. Okay. Currently, I'm telling you this is quite formal. Actually, initially when Janet, this paper written below, they checked it numerically, really using the Ising model, sum over all the boundary conditions with these weights, include a bunch of descendants, do the conformal transformation. You can reproduce almost everything in Ising CFT up to like 5 to 6 sig figs. And actually, analytically, I will show you when we discuss Liouville theory, you can actually even show it analytically, it must be correct. But just from this argument, you can already see it is actually correct. So yeah, any questions so far? Okay, so now this is purely 2D CFT. Now I will tell you where's the bulk. So the idea is to really use some ideas that come from people, the generalized symmetries and the TQFTs. So let me explain. So we will try first rewrite the previous answer as something in terms of 3D TQFT, and that is our bulk actually. So the idea is as follows. For now, I'll first focus on rational theories. For rational theories, it was initially observed by Ronco and then nicely summarized by this work by Fuchs, Ronco, and Schweigert, that the boundary structural coefficients in a very special gauge actually is proportional to the so-called 6J symbols. The quantum 6J symbols, you may or may not have learned it in your quantum mechanics course. It's just some property, it's just some object telling you that when you have multiple, so we have, when you fuse two different spins, representations, then you have the CG coefficient to write the direct product into direct sum. And when you have multiple of them, actually you have different orders when you can do that. And 6J symbols is just the stuff that relate different orders. And it's proven that this is true. And using this property, actually, now I will rewrite the previous partition function by introducing an orthonormal basis I call alpha I defined on all these edges. First, I will collect all the coefficient part. I will call this just whatever it is. I write this part. I call this state psi. The other part is all the position-dependent piece. I will call it conformal block for the reason I just explained. And the partition function will be the overlap and take a limit. So just show you one more diagram. So what this does is, so now imagine my CFT now lives on this 2D boundary, a sphere. I triangulate that. There are these edges. Now I put also normal basis of states on these edges. And I define a state like this. Okay, for the Bragg state is the same. It's pretty cool that when you write it this way, you immediately realize that this is the tensor network representation of the ground state of a 3D TQFT. The TQFT is called Liouville TQFT, or the condensed matter physicists will call it Liouville model. It's a string net model. And the it's exactly the same with this coefficient we chose before to put here. That for the ground state, to match with the ground state. And actually, the physical meaning is also simple. So what this TQFT does is, now for this TQFT is also defined by a triangulation of a 3D surface in terms of tetrahedron. For each tetrahedron, you attach a 6J symbol to it because now there are 6 edges. So on the boundary, originally I have 3 labels for the primaries, H bar, actually just H, and also 3 labels for boundary conditions. But now when I translate that into a 3D TQFT, I just imagine all these boundary conditions extend into the bulk. So now they become a tetrahedron meeting at a point in the bulk. And I will give a contribution of the 6J symbol to it. The actual factors are just making sure that actually after you glue them together, it's independent of the triangulation.
Sorry, I'm
Oh yeah,
kind of lost.
yeah, go ahead. Yeah.
So you say, so I'm with you up to the first equation. Then you say this is the tensor network representation of the ground state of 3D TQFT, blah blah blah. So,
Yeah.
isn't there? Is there which is like what is there a three-dimensional path in the wood here? I'm kind of confused.
Imagine, good. Imagine, say, let's just study the ball, the solid ball. Then the boundary is a 2 sphere.
Oh, you're now all of a sudden you're now thinking of this 2D surface as solid as the boundary of something solid. Okay.
Because when you write it this way, this formula can be interpreted this way. When I invent this state, it can be when you stare at this state, it is the state that you get by performing that path integral.
Oh, okay. All right. Okay. Yeah.
Yeah. Indeed, this is the way the 3D actually pop out. And actually, it looked very random, but I will show you actually now these days it's very easy to do this because in this case, this is the so-called symmetry TFT of this 2D theory. So you can always for a CFT, you can always view it as living on a slab or really 2 boundaries. Another boundary I will explain later, but one boundary is the boundary where you put the CFT, and you collapse the 3D bulk, you get a 2D CFT. Yeah. So for now, it's just an observation, like because you have these formulas and you know, instead of writing the OP coefficient, I will write as 6J symbols, but J symbols are used to construct these states. So I'm just like constructing an orthonormal basis. I can write it this way that this is a ground state of a TQFT. Yeah, does that make sense?
Sure.
Okay.
Sure.
Yeah, sure. But actually, yeah, this is not so strange because if you follow what's recently popular in the generalized symmetry community, this is exactly the sandwich construction, which tells you that in this 2D case, any 2D CFT partition function and correlation function, really you can think of it as living can be gotten by collapsing a 3D bulk, where on one side you put something called the conformal boundary, which in our current case is just given by these conformal blocks. The other side, you put something called topological boundary, which actually, in the current case, is you can it's just giving you this, the path integral of that topological boundary in this 3D TQFT will give you another surface that's very close to the conformal boundary. The overlap just means they are on top of each other, and it's topological, so you can collapse it. So it's really just a way to really literally write down what this overlap means. Yeah, these are this is the original paper that proposing this point of view, and this paper I find it very nicely summarizing this sandwich construction. If you're not familiar, then it's okay, actually, not so important. So yeah, anyway, so by writing it like this, actually, we have reproduced the 3D bulk and writing it as an overlap in 3D. But that's still, the tensor network is kind of trivial. There's just one layer. Now I'm trying to get more layers, and that's from that you actually see the connection to the RG flow. The idea is as follows. So we have gotten a single layer of 3D bulk emerging from 2D TQFT, 2D CFTs. Really, the idea is actually I can perform a symmetry preserving RG flow for a 2D series using the property we just discovered. Namely, I have 6J symbols, I have the OP coefficients, but those coefficients satisfy something that's the consistency condition for them to be a 6J symbol. This is the so-called pentagon identity. You can think of it as the gluing rules of what we call Legos. So what it tells us is the following fact. It's really making sure that the TQFT we construct in 3D is independent of triangulation. So I've told you that each of these 6J symbols is related to a tetrahedron. Now, the left-hand side tells you that you have 3 tetrahedron, and one of its edge is summed over with some weight. So diagrammatically, you have 3 tetrahedron and one shared edge. It looks like this. So when you glue them together, you will get something that look like this. Okay, but you can also calculate as a TQFT. You can say, I don't want to use this method of triangulation. I can also use another 2 tetrahedron, and that's these 2. But when you write these 2 as an path integral, you get the right-hand side. So this is just a way of telling you that it's invariant under this so-called 3-2 Paxton move, which is a TQFT. This is a 3D picture. In 2D, you can also, because I more focus on the 2D boundary theory. So in 2D, using the notation we introduced, the left-hand side, the right-hand side is just 2 triangles, correspond to 2 tetrahedron. And the left-hand side is still 2 tetrahedron, but with an extra tetrahedron glued onto it. The way we do it this way is exactly because you can see written as follows. This is related to the crossing equation because it's really one channel and the other channel. Okay, so
Can I ask you a question? I think so. Tetrahedron for you,
yeah,
is it a solid object or not? Is it solid?
object. Yeah, it's solid.
Okay. So how is the tetrahedron described on the boundary?
It's a triangle with 3 boundary conditions.
Yeah, in the language of the 2D CFT, what is this object? Sorry?
It's the boundary OP coefficient, which has 6 labels.
The boundary.
So just stare at this diagram. On the boundary, each piece you will have alpha 1, alpha 2, alpha 3, sigma 1, sigma 2, sigma 3.
Yes.
The corresponding one in the bulk, you just extend the boundary conditions into the bulk.
But sorry, a tetrahedron is a closed surface, right?
Uh-huh. Yeah. The original 2D BCFT contribution is also a solid triangle, right?
Yes.
Yes. I think you're worried that
clear to continue. Okay, yeah, go ahead.
I think actually that's a good point. The reason why you might get confused is because in this TQFT it looked like all the degree of freedom live on the edge. So the 3D thing seems to doesn't have degree of freedom. That's actually correct. In this TQFT, that's correct. So all the degree of, although it's a solid 3D tetrahedron, actually, but all the degree of freedom live on the edges.
Okay, thank you.
Yeah. Now, using this rule, you can actually find that it's not surprising, but let me just show you. The TQFT, initially I described it, the ground state has a specific choice of triangulation. So suppose I have this. Now, what you do is I have this lattice which is made up of these tiny triangles. But first of all, the left-hand side, I have two triangles up and down. I can use this rule to rewrite it as left and right. And the right-hand side, I also have up and down. I write it as left and right. So now I have this diagram. And the middle two, the edges are glued together. But when you plug in formulas for the 6J symbols, you see actually this is orthogonality. It gives you a factor, which I will show you below. But when you do this, it means that the middle part will disappear. But this immediately tells you that using the moves I just told you, you can actually convert the left-hand side into the right-hand side. This is actually nothing but changing the lattice scale of this DQFT, because you see the lattice scale originally is defined like this. Now it become a larger lattice, which has square root the original length. More specifically, you actually have a factor here, which come from the orthogonality, and also two extra tetrahedron glued on top of it. I will show you the 3D diagram just in a minute. But in 2D, what it means is that you can actually go from a specific representation of the ground state with lattice scale lambda to something with square root 2 lambda with an operation I call U. This is a map between the Hilbert spaces. But if you rewrite the partition function by adding this U back, now I don't have to group the U with the psi. I can group the U with the omega. And I will define that as my omega on this larger lattice. So let me just show you the 3D diagram. What it means is as follows. So originally on my boundary, I define my surface to have triangulation on the scion edges. So there are 4 of them. Now using the rule, I will have 2 extra tetrahedron, which is the shaded one here. But now you can contract the indices of these scion lattices, the scion edges with the shaded tetrahedron. And it will give you an edge actually live on the green line. So the CFT actually originally I have a state defined on this short edge. Now I have a state now defined on this green edge. In the boundary CFT, this is performing the real space RG flow because it's changing the lattice scale. And in the bulk, I'm actually by this contraction moving into the bulk. And this is exactly the UVIR correspondence in ADS CFT. By doing this procedure again and again, you can actually go deeper and deeper into the bulk. And that is the tensor network that people usually draw. And I actually will show you that these edges now here are not random. There are physical meanings attached to them. They are the geodesic lengths. Just one more diagram to show you, and you can ask questions. The 3D picture, I think most of you probably are not so familiar with the 3D TQFT story. Let me just tell you, actually in 2D, this story is surprisingly simple and actually quite beautiful. So in 2D, yeah.
Good question. You're talking about geodesic lengths, right?
Yes.
In the bulk, you have a topological series.
Good.
I'm confused.
It's really because, yes, without the boundary, it doesn't make any sense to say it has length. It's like in, let me see how to say this. All the notion of length actually come into play because your boundary breaks topological invariance.
Is there some sort of metric encoded in the boundary? Is there
Yes,
both?
you should think of it this way. The distance, yes, the distance, the metric, they all become real when you put it when you attach that boundary to the TQFT. 3D gravity must work this way, right? Because ADS3 is the classically it's just Chern-Simons theory.
I see.
Yeah.
So I see. Okay. Thank you.
Yeah. This picture, let me tell you the 2D story. Actually, I think this is more intuitive, but just not to get you confused. But now it's a good point to go back. Actually, why don't we study the 2D? We are actually trying to say the story. Actually, for JT, it exactly worked this way. And the picture is nicer. The idea is as follows. So now the 2D, 1D partition function would also be written as an overlap. So you have a TQFT. So the ground state is prepared by passing on disk. So now I also do triangulation. I wrote alpha here because I have diagram-written theory in mind. If you don't know what it means, it doesn't matter. It's just a TQFT, which previously we had tetrahedron. Now it's just these triangles. So the states are defined on these boundary edges, which I call G1, G2, G3. So the bulk path integral will give you a state living on G1, G2, G3. The 1D partition function can be calculated by taking the overlap with another 1D state that also defined on these edges, which I call omega. The omega states, you can think of them as previously I used conformal blocks. Now it's probably just even simpler. It's related just to the boundary length, for example. So, okay, now, but what does the previous RG flow mean? It just means that now, first of all, this is a TQFT, I retriangulate that. So originally I had these two triangles, for example. Now you retriangulate, you can draw it as one on the left and one on the right. But when you have this one on the right, you can now contract the omega indices living on G1 and G2 with this triangle. It will give you an edge living on this red curve. So what you do is the omega will now be defined on this red line. And this operation will perform an RG step for this omega. It will also move you into the bulk. And you can keep playing this game that will give you the mirror type tensor network for you. And actually, this is the tensor network renormalization community actually knows this, I think. It's just not so appreciated by the high energy physicist community. So yeah, does that make sense actually? Okay, I hope it does.
Yes.
So yeah. So let me just say a little bit more. So actually, what are we doing? In each of these RG steps, what are we actually doing? We are actually adding entanglement to this state, omega. So why do I say that? How do I see this actually? The most simple way to see is originally you can try to find say the bound dimension of the left hand side and the right hand side. You can see that for each of these steps, actually the bound dimension will grow. And when we perform keep doing this RG flow, the bound dimension will keep growing. Okay. And the omega state we constructed, actually, because they are coming from conformal blocks, it's very natural to expect actually this is at the fixed point of this RG flow. And indeed it does. How do I see that? It's because now I have infinitely many descendants, and that will give you infinite bound dimension. And that's the intuition why you should believe this is RG flow. You can actually check it very explicitly by showing actually this reproduce the CFT partition function. The idea is now I draw this diagram again, but now they become dashed lines. Dashed lines means there are also these position-dependent conformal block pieces. But previously, for the triangles, you actually spit out the tetrahedron. But the tetrahedron, they are also proportional to the Virasoro crossing kernel. The crossing kernel is exactly the stuff that can be absorbed by these conformal blocks to transform nicely. So when I write these equations, now they really become equalities. The extra factor, the factor coming from the coefficients will be absorbed by the blocks. So finally, the left-hand side is equal to the right-hand side, telling you that the overlap is invariant. Or you can say it's a fixed point. And indeed, it reproduced the CFT partition function. And I will tell you that this is very magical because now you see actually these OP coefficients or 6A symbols, it's very crucial they play three different roles. The third role is they are also proportional to the Virasoro crossing kernel. Yeah.
Sorry, just a quick question. When you're talking about the connection to renormalization group and tensor networks, you have in mind the approach which is basically tensor network renormalization for path and Euclidean path intervals, right? Which
Correct.
is distinct from, well, could be related, but at the moment distinct from Mira or things of that kind.
It's not that yet. And I will show actually there is just in the next slide. So how it's related to what people usually say.
Thank you.
Yeah. Indeed, very good question. Usually people don't talk about the tensor network for the space-time Euclidean path integral. Usually we talk about the tensor network for a state. But really what you should do is not so different. What you do now is instead of looking at CFT on a closed manifold, which gives you a function, now I study CFT where you do the path integral on something with a boundary. So when you do that, just imagine you want the ground state, for example. The ground state of a CFT is defined by performing the path integral on a disk. Now, you should imagine doing this path integral on the bottom of this disk. This gives you a state on this red circle. And well, it's a Euclidean path integral, but just from what I told you, actually there's a 3D stuff, which is now the tetrahedron. They meet on the top of this. There's another surface, another 2D surface on the top of this whatever you call it, the boundary of a ball, the S2, and that's where actually you get geometry. That's the time slice. So the magical thing is that the direction, the R direction of the Euclidean path integral in CFT is the same as the Z direction of the gravity path integral. So using this perspective, you still do the Euclidean path integral on CFT, it will give you a tensor network for a fixed time slice. But it's more like Chris Akers recently have a paper. They call this the bottom one where you have the CFT is more like the worldsheet. The top one where you have like this target space. Yeah, I hope it makes sense. And yeah, sorry, yeah.
Sorry to interrupt. When Giffrey and friends formulated this tensor network path integral, tensor network normalization, they also argued that on the boundary, if you have a boundary on the boundary, it will give you something like mirror. But they also made the observation that that only really works if you have a discrete system, if you have a lattice system, and in the continuum limit, we don't really know what happens, right?
Yeah, that's a very, very good comment. I think the real reason is as follows. Yeah, this whole procedure is very counterintuitive. You might think it's impossible to realize a CFT using a lattice, right? The reason why it avoids all those statements is because the bound dimension now is infinity. It never works.
Or not?
It is infinity. Because I have infinitely many descendants. Otherwise, it's impossible to get a fixed point. That's also, yeah, you might have pure objection that this doesn't look like mirror because it doesn't have a disentangler. But I think that's exactly the same issue. When you have infinite bound dimension, you don't need those stuff. Some no-go theorems can be avoided.
Okay.
Yeah. Yeah, very good question. Thank you. So indeed, in this case, as I already showed you that this is invariant in the retriangulation because this is just crossing, right? You can use this freedom to actually construct a tensor network for the vacuum, prepared by the Euclidean path integral that look like this. And you can even use that to calculate entanglement entropy. We try to calculate the most simple one, the single interval one. It matches, of course, because it's universal. And indeed, it would be interesting to study more general ones. And we haven't done that yet. So yeah, I don't know what to say. Comment down. But okay. Let me just make a quick comment. Everything I described to you looked very nice. It matches what you might have thought about tensor network, the connection with gravity, but it only looked like it is gravity. But now I will show you actually using Liouville theory as a very explicit example. This is really constructing quantum gravity for you. Especially, it's not semi-classical gravity; it's quantum gravity. It gives you a quantum theory with the non-perturbative measure. So first of all, to study Liouville theory or really more realistic gravity theories, you have to deal with the fact that those theories are irrational. The previous ones, I use sum. Now the sums all have to become integrals. And it's actually not known at all whether the same relationship between the OP coefficients and 6J symbols are correct for those series. And because they are integrals, it might diverge. And a more severe issue is that Liouville theory, if you have studied that before, it doesn't even have a vacuum in the physical spectrum. So the procedure seems to be doomed. And indeed, we spend a lot of time seeing that actually everything works. So first of all, I will tell you that nowadays it's kind of becoming popular to use this normalization for the bulk operators, but really you can actually normalize all the boundary operators like this. If you study Liouville theory, you know there is a reflection coefficient. You divide it out by square root. This is nice because it makes the reflection under alpha goes to q minus alpha invariant. This operator looks more Hermitian. If you don't know what it means, it's fine. But just trust me, those formulas are all known. Using this new normalization, actually, it's surprising to us that it almost takes exactly the same form as rational theories. There is a bunch of 6J symbols constructed by Teschner and Ponsot, which are called the 6J symbol for the modular double. It's a very special representation of this quantum group UQSL2. If you use that 6J symbol, which was argued to be related to hyperbolic geometry, and you use the OP coefficient described using my prescription of normalization, you find this formula. The proportionality constant now is this mu. What is mu? Mu has 3 different rows. I think it's important, so let me just explain it really quick. So the 3 rows are as follows. First of all, as quantum dimensions, a generalization of quantum dimensions, they are the so-called Planck measure of this quantum group. Okay, never mind if you don't know what it means. But when I write it out, this formula actually is the Carty density of state. So that's the second role played by it. And if you remember how the Carty density of state is derived, it is the modular S matrix. So really this factor here, it plays these triple roles, and you should just plug it here. It's the natural and correct generalization of the quantum dimension in rational cases. Okay, so the first step is fine. The proportionality is still correct. The second step, we have to really make sure that we can close the holes and make sure it's convergent. Also, you might complain there's no vacuum, right? What do I mean by I want the vacuum to pop out? Actually, surprisingly, if because we have seen that the Planck measure plays similar role as the quantum dimension. Let's just try to guess that this is the correct weight I need to plug there. So if you do that, you can calculate this diagram. This diagram has 2 OP coefficients and 2 conformal blocks. We write it out, do the weighted sum, it looks like this. So you sum over complete spectrum in alpha j, alpha k, and use weighted sum over this boundary condition. And the OP coefficients are here. There is also a conformal block because you sum over all the descendants. Now you plug in the formulas for C. Okay, oh, sorry. When you do that, you immediately see that some magic happens. These coefficients, they combine themselves very nicely into the Virasoro fusion kernel again. They're proportional to the Virasoro fusion kernel, which turns some object into the vacuum channel. Although the vacuum is not there, this formula is equal to the vacuum related formula. So, and there's a orthogonality when you perform the other 2 integrals. So when you really plug in all the formulas, you see this, the final calculation becomes this. You get 2 states. There's a vacuum module propagating here, and there is a very tiny bubble with identity because of this dual this fusion kernel. Because it's so tiny, when epsilon goes to 0, the imaginary part the imaginary part go to 0, it again gives you this divergence piece. It tells you that you can remove this bubble by dividing out this factor. Again, in this case, actually use this weight, you can again shrink the bubble. It's exactly analogous to the rational case. And you can write the, sorry, I forgot to write it actually. The path integral again as an overlap. So that you can play the same game. You can reconstruct, using this theory, you can reconstruct that a tensor network that look like ADS3. Really now the last step is to say it is ADS3. So what do I need to check? I just need to check that actually this bulk term, which is coming from the side, actually has Einstein-Hilbert action in it. Okay, it's just this is the wave function. So especially ADS3 is special in the sense that all the solutions are locally diffeomorphic to ADS3. So I just need to make sure that in large C limit, each triangle is some sort of Einstein-Hilbert action hyperbolic space. And for the Angsha actions in 3D, it's proportional to the volume because you can plug in this R is constant, you plug it in, it's just integral square G, so it comes to volume, it's this guy. And interestingly, if you study the large C limit of this 6J symbol, it's also exactly equal to the volume of the hyperbolic tetrahedron, whose length whose geodesic length, hyperbolic tetrahedron just means a tetrahedron in hyperbolic space where all the lengths are geodesic and the lengths are labeled by this Li. So you also see that the physical meaning is this. Yeah. Yeah, okay. And there's an extra term, but this extra term is actually good because let me just say before I say that, I will just tell you there's a similar formula in literature that relates the 6J symbol to the hyperbolic volume, but in terms of dihedral angles. But it's actually very magical that just do some math, you will see that there are some magical identities in hyperbolic geometry that can relate these two kind of volumes. And the difference is exactly given by this term. But this term actually should be there because it is the so-called Hayward term in gravity. So I think most people are not familiar with Hayward term. It's just a term like when we study the variation problem in Einstein gravity, we know that the variation problem, if you only have the Einstein-Hilbert term, is not well defined. You have to add the Gibbons-Hawking term. This is similar. So now if more than a boundary, now if you have a codimension 2 corner, the variation problem is again not well defined. You have to add one more term, and this is the term. This is discovered by Hayward. That's why it's called Hayward term. And this term is there. That's good. That matches the expectation value with gravity. Now let's try to see what will happen if we combine everything together. So let me just draw around this line, which I call the sigma, which is now you should think of it. Yeah, it's an edge, and I also have this mu factor, which is the Plancher measure. The large C limit. Oh, sorry. The large C limit is known. So when you combine them together, you see these guys actually combine into the volume, the Einstein-Hilbert action, plus a term that's 2 pi minus theta times L. It's actually this is the discrete version of the curvature. Actually, it's a conical singularity if theta is not 2 pi. But for smooth ones, which actually are global saddles, this theta add up to 2 pi. So we are actually summing over a lot of geometries by including the fact that what I told you is for fixed lengths, but I also have to sum over all these weights. Okay, when you do the sum, you are summing over all possible geometries. Of course, the saddle will come from the global variation problem, which sets all of these to 2 pi. Right. So this is really a sum over geometries. And as you see, the 6J symbol is not a large C quantity. It extends to all orders non-perturbatively in C. And it's actually very crucial to have this to have a non-perturbative because you want to satisfy the pentagon identity such that bulk does not depend on the triangulation. So the finite C corrections are all very important. And I would say because by construction, the boundary can be written this way. It has a bulk interpretation. It actually, you should view it as defining a non-perturbative measure for a quantum gravity theory that matches exactly with a CFT. Liouville theory is kind of stupid because the gravity theory only have graviton. It doesn't even have black holes. So it's a kind of exotic, trivial gravitational theory. But for more realistic CFTs, which we currently don't know the OP coefficients, you should expect that this procedure will give you a definition for a non-perturbative quantum gravity theory to match with the CFT. And yeah. So with that, I want to say that this is the end of my talk. So I've talked about four things, a four-step procedure to construct the quantum spacetime starting from 2D CFTs. First of all, you can triangulate the 2D CFT, and you can calculate the exact path integral from a triangulation procedure. Then from that procedure, you can write it as an overlap. The overlap has a close connection with the 3D TQFT, which is closely related to the topological symmetries of the theory. Then that gives you a single layer of bulk. Then you can use the topological symmetry or the property of the 6J symbol to grow more and more layers in the bulk. That gives you a 3D tensor network. And finally, we show using Liouville theory that this tensor network is giving you what you expect for quantum gravitational theory. And more importantly, it's defining a non-perturbative measure for it. So there are certainly some very important future directions, some of them we are trying to work in recently. The first one is as I said, for more realistic CFT, the relationship between the boundary changing operator OB coefficients are just not known. So it's very hard to make progress. So you might want to look at a realistic holographic CFT like the D1, D5 CFT, but those OB coefficients in the is not solved numeratively, so you cannot do it that way. If you have, I believe it will work. But what we can do for simplicity is to do ensemble average of, suppose I have a lot, is the philosophy people recently use a lot. Suppose I have a lot of large CFTs, then you can try to average do ensemble average over the 6 symbols. And actually, the ensemble average of the boundary coefficients are actually known. So using that, we actually checked that for the torus, it's pretty nicely giving you the vacuum ADS and the BDZ black hole solution in the sum. So it's kind of the universal emergence of 3D gravity from this perspective. And next, of course, more interestingly, partition function, you might say is boring. So also it's Euclidean path integral. So can we actually do Lorentzian signature? There are multiple subtleties. Some of them are related to causality, some of them are not. But ultimate goal is to really understand in this formalism, if tensor network is really useful for describing non-perturbative physics, we want to use it to understand black holes. So actually, we have some ideas, even using Liouville theory, because you might be surprised because I told you Liouville theory doesn't have black holes in it, but actually some Liouville boundary states have black holes in it. And that's a paper I proposed with Wan Zhen. You can actually use the so-called ZZ boundary state to study black holes. And we're actually trying to see if there is a non-isometric map somehow when you have a Python type geometry. The next, of course, as Nima originally pointed out, partition function is boring. So definitely you want to study correlation functions. So how do we reproduce, for example, the 2-point, 3-point functions we're currently trying? Our boundary is known. It's just the difficulty is really to do these calculations. The conformal blocks are not known. Versor conformal blocks are very complicated. So we're trying to make some approximations to see matches, for example, with the geodesic approximation, whatever. The next thing is actually the philosophy I told you, just use the bulk. It actually seems very natural. It's not only work for ADS. What's special for ADS is it has a boundary. And the boundary seems to be a natural place where you put the endpoint of your RG flow. But bulk theory is topological in 3D. And can we actually use this method to make sense of de Sitter gravity or flat space spacetime? Especially one motivation for doing this is because nowadays people like to study the double scale SYK, which is related to de Sitter gravity. It almost share very similar structures to JT gravity, which is related to ADS gravity. And I think we have some ideas, but still trying hard. The next is definitely we can use this to study the wave function tensor networks people usually talk about, but we haven't. I think it's quite powerful and definitely it will be useful to study. It seems to provide some tools to calculate the entanglement, but for multi-intervals, it's actually hard. One reason is because the blocks are very hard to compute. But really, can we use this method to see why the root Takanagi formula, for example, for multi-intervals are correct? We are trying nowadays. And the last thing is definitely you might want to ask me, 3D gravity is so special. Excuse me. Because the bulk is topological. Semi-classically, the action is just 2 transamination series. So can we actually do higher dimensions? Currently, I have no idea. Janet, they tried something using some simple TQFTs. But actually it's never giving you something as exotic as gravity. So I leave this really as an open question. And I don't know any more to say about it. So with that in mind, thank you for your attention.
Thank you so much. Are there any other questions?
Can you try to add matter to the topological theory in the bulk, so put extra degrees of freedom on the links and see what happens?
Yeah, very good question. You can imagine doing two kind of different things. you can add, yeah, let me say both to you. So you can add matter both either on the boundary or in the bulk. So on the boundary, you couple Liouville to, so there are two different type of matter fields. You can add a probe matter field. I think that using Liouville field is enough to describe, because that's just a word line action. Essentially, it's just a Wilson line. So for that, that's fine. Just add a local Liouville operator that our framework can explain that. But if you really want a back reaction, on the boundary, you will couple the Liouville series to other series. And for those series, yeah, I think it is indeed a very interesting question how to, because in that case, the whole theory, the 6J symbols doesn't work so nicely as currently. And I'm actually not sure if I can use just a subsector to go deeper into the bulk. On the other hand, you can also ask another question, which is, in the bulk, can I directly couple it to bulk matter fields? I think that's somehow related to what Chris Akers and Ronak Soni and Anyway recently have a paper. They have a proposal. They consider some situations where you can add matters. So yeah, I don't know currently using our formalism how that's related. But indeed, I think that's a very interesting question.
Any other questions? I have another question. So you had a comment about non-isometric maps, but
Yeah.
nothing about what you said was isometric, right?
Sorry?
None of, with all the tensor networks you described, none of them were isometric. I don't see any reason for any isometric setups in your discussion, right?
Um,
I think the guy already left.
let me see how to put this.
So Euclidean path integral tensor network normalization is non-isometric,
Yeah.
right?
It really depends on, let me see how to say this. If you throw away stuff, then it's not. But I believe when you talk about fixed point, actually it is. Because you don't throw away anything, right? It's
I mean, you have to show that it's an isometric map.
yeah, definitely, yes, yes.
Group in the sense of Euclidean path interval tensor network normalization in full generality, even for free fields, is non-isometric,
I see.
right? That's just, I mean, that's the stuff that Giffrey and friends have done. And I mean, as far as when we were talking Euclidean path integrals, there's no clear role for isometry.
Why is that actually?
Why would it be? I mean, there's no time evolution. There's no, like, these, you're just sewing. You're sewing states. And every time you have to normalize again, right?
Ah, I see what you mean.
When you sew two path integrals, right, on an edge, you have to normalize again. Nothing
I
tells
see what
you
you
that
mean.
your state
I
will
see what you mean.
remain normalized.
I see. Um, yeah, that's right. Yeah, I had to think of it. Actually, I kind of, let's see. Actually, um, in using the 6J symbols to do normalization, to do renormalization.